Hello again, this is John Michael O'Brien. You're watching the third video in a series of videos about LED illumination for cosplay, and really for anything in general, but cosplay is the most common use for it. So, if you didn't watch the first two videos, in the first video we talked about the simplest configuration. One LED, one resistor, one battery, and then just simply copy this. You don't have to copy the batteries, but you do have to copy the LEDs and the resistors. In the second video, we talked about putting more than one LED on that same resistor, and when that works, and how to get basically more light for the same amount of battery power. Now we're going to take it to the last step. This one's the tough one because it turns out that guy don't work no more. So, we talked earlier about LEDs and they have a constant voltage drop. Okay, so that forward voltage, like on a blue LED, about 2.6 volts. The thing is that that's not quite true. See, it turns out LEDs have this relationship between their voltage drop and the current that runs through them that looks more like this. Well, if we talk about, that 20 milliampere point, basically we're picking off a point here and then reading off here 2.6 volts is equal to 20 milliamperes. Now the thing is that we can pick other parts on this curve. We don't have to be at that spot. That's the ideal operating point for the diode, and usually you want to pick that. But the problem is that picking that without having exactly the right battery is problematic. You essentially have to put some kind of current limiting resistor to keep it from wandering way over here. If this is 9 volts and we set a 0 for the resistor here, and these are all 2.6 volts, we do 2.6 times 3, come up with a number, 2, 4, 6, 7.8 volts, and there's this 2 volt error, which pushes us way up here in the current, and that causes the LEDs to pop. So, that doesn't work. However, we can take a little trick and make that still work for us. So let's imagine, again, our hypothetical LEDs. We're going to use 3 volts, but we're going to pick a slightly different number just to make it more apparent exactly what has to happen. We're going to use 10 volts instead of 9 like we have been. So, but these are our standard 3 volt LEDs, right? And from our previous conversations, we know then that the 3 of them have to add up to less than 10 volts. Well, if we do 3 of them, or not 3 of them, the sum of all the LEDs have to add up to less than 10 volts. Well, we got 3 of these guys, that's 9, right? Well, that means we have to put a resistor in and calculate the leftovers. Well, we don't like resistors. Resistors take up space, and literally they waste power. All a resistor does is turn electricity into heat. The less of that we do, the longer our batteries will last for the same amount of results. So there's a trick. The trick is you go 1 diode more. And you can do more than 1, but there's a whole bunch of math that goes into solving where you land on this curve. Trust me in this one. 1. Go 1 diode over, and then finish up the circuit. No resistor. The thing is, this circuit now has technically, so if we were solving it the way we were doing it before, we'd say 3 volts, 3 volts, 3 volts, and one last 3 volts here, for a total of 12 volts. And remember, Kirchhoff's voltage law says these two must add up. They don't. However, and then here's the trick. So if we take and imagine that the voltage drop across all the diodes is even, and that's largely true, and if you don't have to design stuff that's going to last a million years, you can take that assumption to be true. The trick here is that we actually know we have 10 volts divided by 4. Since we know we're less than here. Matter of fact, even if we weren't less, it would still be true. It's just that the currents would get ridiculous. So what we actually end up with is about 2.5 volts per LED. Well, let's say we were still on this curve. 2.5 volts is about here on that curve. Which we'll come over here and we'll draw like 10 milliamperes. The exact number is very unique and will depend on your diode. For that matter, there's actually a lot of variations to exactly what number you get out of this, even within the same diodes. If you get 3 different groups of them together, what number you get here is going to vary pretty strongly. However, turns out the amount of light that a diode produces is linearly proportionate to the current you run through it. So if we do half the current, we get half the light. So you think, okay, well that's terrible, we've got half. There's a trick. It turns out human vision, our eyes, see a difference of 10-fold. So the difference between, say, a 100-watt light bulb and a 10-watt light bulb is about half, is the way our eyes perceive it. So what this means is that this is half, which means our eyes actually see it as almost identical. So the trick here is by doing this, we get about half the light, draws half the current, which actually works out in our favor and produces almost the same light. Now, almost. These will be dimmer, period. That's the thing we're giving up for this. We get rid of the resistor, we get rid of all the regulation and all the other parts, and we get dimmer lights. But the dimmer lights won't be that much dimmer. And if you find LEDs that are way brighter than what you really need, and those these days are actually getting to be really common, you can use this trick to get the amount of light you want, just simply, and do it without the wasteful resistor. So now we're, instead of getting, before we had one LED per battery connection. So 20 milliamperes, one LED. Here we had 3 LEDs, 20 milliamperes for 3. Now we've got 10 milliamperes for 4. Now you think, okay, well, why not put 10 over here? Well, we could. We could actually tone down the LEDs, and if you have really bright LEDs, you can do that, and it will work. It will exactly work. But if you're trying to rule this extra resistor out, so take the part count down, make it easier to put together, make it more reliable, because there's less stuff you gotta solder. Now we've got 4 LEDs for the same voltage. If I had to put 9 volts here, it would have been, the numbers would have been too convenient. 3 times 3 is 9. That's why I picked 10. But the actual basis of this still works out to be the same. So this gives us 4 for every connection to the battery, at a slightly lower current, and by extension, slightly lower light. But when everything's said and done, we get a much better result.